It seems like you could just add a bunch of links to a LAN to add capacity, but spanning tree ends up blocking on most of those links. However, if you then add EtherChannel, you can get all of those links active at the same time. In this video, we'll walk through how that works and how to configure it. Let's go. Well, as it turns out, I've put EtherChannel in 2 different chapters of the current editions of my books. Just be warned, you'll see those in Chapter 9 and Chapter 10 of the current edition. But for this video series, I've put all of EtherChannel into this one video. And so what are we doing in this video? Well, first we'll talk about the need for EtherChannel. That is, why does spanning tree block on most of the links between 2 switches and how EtherChannel overcomes that. Then I'll show you how to configure what I call a static EtherChannel. That is, you configure it and the links are always in an EtherChannel, although iOS will say which ones are active and which ones are suspended at any one point in time. Then we'll talk about this idea of a dynamic EtherChannel in which iOS does additional checks before adding links to the EtherChannel. And then we'll end with a verification Palooza where I show you bunches of show commands and show you what the status would be when things are working and when things aren't working so well. All right, let's get into it. Imagine you've got this pretty typical campus LAN design, and I'm only showing 2 access switches, but you could have a bunch of them. And down there on the access switches, we have some endpoint devices, and let's just say, for the sake of argument, those ports are all 10, 100, 1000 ports, most of which are running at 1 gigabit per second, right? Let's say these are older switches, and all those links between switches are also 1 gigabit per second. And if you look at that, you say, that seems bad, right? And it is. There's this idea called oversubscription, where if you've got, say, 24 1 gigabit ports on all these access switches, we'd expect most of their traffic to go up, northbound, toward the distribution layer. And you don't want all of that 1 gigabit per second traffic times 24 ports to be trying to get out this single 1 gigabit per second link. You'd think, as a network engineer, I want more capacity, more speed, more bandwidth going up toward the distribution layer on those uplinks. So one way to improve your LAN would be to upgrade those uplinks to, say, 10 gigabits per second. But it could be your current switches don't have ports that run 10 gigabit per second. So what do? You take out the old switches, you put in some new switches, you spend that little bit of money, you buy switches that support 10 gig, and you upgrade all your links between switches to 10 gigabit per second, and that would be a great migration path, and we can totally ignore EtherChannel then. But an alternative to that is to say, hey, we've got some spare gigabit Ethernet ports on these same old switches. Now we're back to the old switches. Let's put 4 links between each pair of switches. Each of those run at 1 gigabit per second each, but you can think of that as 4 gigabits per second of capacity between each pair of switches. We've solved the problem, right? Well, it turns out you haven't totally solved the problem. Here's what happens. Let's zero in on one pair of switches between D1 and D2. And by the way, I placed a couple of example endpoints out by D2 just to make a couple of points. Here's what happens if you just add these links without any EtherChannel logic. You turn up those links, spanning tree takes over, and spanning tree is going to end up blocking on 3 of the 4 links, maybe 4, but let's just say it ends up forwarding on this one. Well, it's going to block on the other 3 just because how spanning tree works. If it didn't, you'd have a loop, say, going in and out of gig 101 and 102. So it's going to end up blocking there. And what EtherChannel does is avoid letting spanning tree block on those other 3 ports, in this case, making all of them active at the same time. To help explain how that works, take a look at this MAC address table on switch D1 that I've got showing here below now. We're still in that case where we're not using EtherChannel, and let's say PCs A, B, C, and D use these MAC addresses that have a bunch of A's, B's, C's, and D's in them, all right? So from a MAC learning perspective, because 3 of these links are blocking, all 4 of those MAC addresses are going to be learned off of D1's port gig 101 because the other 3 ports are effectively unused at this point. So enter EtherChannel. What we'll do is we'll configure so that all 4 of these ports are considered to be in the same EtherChannel. That configuration will exist on D1, and we'll have similar configuration over on D2. So both of them treat all 4 of these ports as if they're together. Now the feature we call EtherChannel, but the interface that we create in the config to make all this work, it's called a port channel interface. So it changes what the MAC table looks like, and it changes how Spanning Tree views the world. First off, Spanning Tree is going to operate on this port channel interface rather than the underlying physical interfaces. So Spanning Tree is going to give port channel interface a Spanning Tree port role and port state, and the port channel interface itself is going to end up in a forwarding state. And when it learns MAC addresses, those MAC addresses are going to be associated with the port channel interface. And then we're going to have other underlying logic. All right, so let's take a look at that MAC table. Here are the same MAC addresses for PCs A, B, C, and D. And those MAC addresses are now going to show that they're learned off of port channel 1, which is kind of interesting. So if you start thinking through, well, what's going on under the covers if a frame arrives from somewhere off to the left and it's, say, headed for PC A, the MAC table will be matched and the outgoing port is port channel 1, but which physical interface does the frame get forwarded out? Well, there's that additional logic, and we call that the load distribution algorithm for that ether channel. And there are configurable options for how that happens. But for the sake of discussion, let's just say the load distribution algorithm is distributing things based on the destination MAC address. That's one of the options. So that load distribution algorithm would say, hey, MACs with a certain bit pattern in the low order bits of the MAC, some of those get sent out gig 101, and other bit patterns out gig 102, others out 103, and others out 104, the 4 ports in this port channel interface. And maybe, as it turns out, because I picked MAC addresses that are just a couple of bits off in the low order bits, maybe they'd even get distributed over these 4 other interfaces. Interesting, huh? So it's just a way to load balance based on destination MAC, in this example, what goes out over the ether channel. So what do we get? We get no blocking on those 4 interfaces. We get these port channel interfaces showing up in our MAC address table, and we get to use all 4 interfaces at the same time. Just to be complete, here's a list of some of the common load balancing algorithms you can choose via config. For instance, there are 3 that are based on layer 2 information. You could balance based on the source MAC of frames, or the destination MAC like we just saw, or the combination of source and destination MAC. And again, what the switch would do then, when it comes time to pick an individual interface, it looks at the low order bits in these fields and just looks at those and say, hey, I'll take a bit pattern of these 2 bits and say, you go to interface 1, you go to interface 2, 3, and 4, and so on, just to balance the traffic based on those values. There are options where it actually looks at the IP addresses, the source, destination, or both IP address, and even the layer 4 port number fields in the TCP header, just the source, just the destination, or a combination of both there as well. So let's see how to statically configure an ether channel. We'll use 2 switches with just 2 links in between them as a backdrop. Now, terminology-wise, the feature is called ether channel. The interfaces that get created are called port channels, and they'll have a number as the interface ID, not with slashes, just a number like port channel 1 and port channel 2. So right off the bat, do these numbers on opposite switches, these neighboring switches, they do not need to match, all right? So I showed them as 2 different numbers. Now, if I was doing it, would I make them match? Probably, all right? But they don't have to match. Now, the underlying physical interfaces, gig 1013 and 1014 on the left, 1015 and 16 on the right. Clearly, they don't have to match either. Now, if you have the opportunity and open ports to make the numbers match, would you? Yeah, maybe you would, just for easier operation, but just making the point, they don't have to match either. Now, as I said, the port channel interfaces will be created for you potentially, or you could just type the interface port channel 1 command on D1 to create it. But most normally, people instead configure this way. They create the config for the port channel interface by typing the channel group command under the physical interface as a subcommand. So it's yet a 3rd term. So the feature is ether channel. The interface that we'll see in the MAC tables and the like is the port channel interface. The command to add an interface to the port channel is channel group. So this command means add this physical interface to port channel interface 1. Mode on says statically configured. I'm not doing anything dynamic. Place this port into that port channel 1. And you do that on the two interfaces, 1013 and 1014, and both are added to the port channel 1's ether channel. Yeah, a lot of mixing and matching of terms referring to the same big ideas here, unfortunately. That's just the way Cisco chose to describe it. As a side effect, though, of the first of these channel group commands that refers to the number 1, iOS then creates for us dynamically that port channel interface. So you do a show run after all this, you'll see interface port channel 1, and it will exist in the config. You can do a show interface port channel 1 and see statistics. Other commands will refer to this port channel 1 interface. Now we're halfway done at that point. That's the switch D1 side of it. We need matching config over on switch D2. So here on switch D2, we'll get into interface config mode for 1015 and 1016. Channel group 2, because it appears from the diagram we want to create port channel 2. Maybe we've already got a port channel 1 connected up somewhere else there. So port channel or channel group 2, mode on, meaning statically configure these ports to be in port channel 2. And the first of these will dynamically create or cause the switch to dynamically create port channel 2 over there on switch D2. Now I just gave you a lot of rules, so some of those are repeated up here in the first section. I also mentioned here at 2.1 that if we use mode on, that statically configures the channel. That is, we're placing these ports into the channel. There are a couple of other dynamic options that add additional checks, all right? There's one based on a Cisco proprietary protocol called Port Aggregation Protocol. It's not mentioned in the CCNA exam topics anymore, but if you see modes of desirable or auto, you should think PAG-P. And there's an IEEE standard that Cisco prefers these days. They came out after PAG-P first came out. And if you see keywords active and passive, that's a clue that you're using LACP, and we'll talk about that in the next section of this video. There's also some checks that happen on all these, whether static or dynamic with either protocol. And those are the checks that we'll talk about here in the next few minutes. These are checks of settings on the physical interfaces that must match amongst the physical interfaces for them to be active and used inside the ether channel. So let me walk you through a few variations on the config so we can talk through that. First off, I'll call this example 2. It's the exact same config as before, but we have a subcommand on the physical interfaces when we start. Both these sub-interfaces, or both of these physical interfaces have a switch port mode trunk command. Notably, they're the same command and they match. So what's different here? We've told the switch, hey, these ports are trunking, which is probably going to be true between two switches anyway. We configured the channel group 1 command with mode on to say statically trunk. The switch automatically creates the port channel interface, but notice it even copies over the subcommand from the physical interfaces when it creates the port channel interface. It indeed would do that. That's something you could experiment with in lab even, and I encourage you to do so. All right, so there's one example. How about this example 3? Here we start out with two interfaces with two relevant subcommands, switch port mode trunk and switch port trunk native VLAN 3, overriding the default native VLAN of 1. And we've got those same two commands on both physical interfaces. All right, so when the first of the two interfaces, channel group 1 commands, is executed, iOS creates that port channel 1 interface, and it copies both of these relevant interface subcommands over to the port channel. See the pattern here. So when that port channel is first created, it copies over those commands. So guess what? The relevant, and I keep saying relevant, the relevant interface subcommands need to match on the physical interface. In fact, iOS is going to check to make sure those things match up. And if you configure them differently, it's not going to work correctly, or some of the links may not function within the ether channel. For instance, here at example 4, we're going to show a broken static ether channel config. So we'll start out with those same two interface subcommands of switch port mode trunk and switch port trunk native VLAN 3 on the top interface, but I put a line through them at the bottom to signify they don't exist on port 1014. But we went ahead and configured the channel group 1 mode on commands in each case. So what happens? Well, if we type these in the same order shown here, when this channel group 1 mode on command, the first one was executed, the switch would create this port channel 1 command with these two subcommands. And then when it tried to add this second interface to the channel, it would say, well, I will keep track of it and think of it as part of the channel, but I won't actively use it because its config does not match up to what I've put on the port channel. It'll be in what's called a suspended state. So you're probably sitting there thinking, come on, Wendell, what has to match up? Well, here you go. Of all the links on one switch, so this is a check done on a switch, like on switch D1. It'll check all the links you try to add into that ether channel to make sure the link speeds match and the link duplexes match. Its operational state as an access or trunk port. In other words, both of those links need to be access ports or both need to be trunk ports on that one switch, or all 4 or all 8 or how many ever you put into the ether channel. If the links, all of them are operating as access ports, their access VLAN numbers must match, right? So if they're in access VLAN 10, they've all got to be in 10. If it's operating as a trunk, all those ports, they need to have the same allowed VLAN list configured, and they need to have the same native VLAN. We saw the native VLAN in that latest example. Additionally, there's an idea that a switch port acts as a switch port, and we call that a layer 2 or switched port. And I haven't even talked about that in the course yet, but that's kind of the default operation of a port on a switch, to act like a layer 2 switch's port. But there's a way you can override that setting and say act like a router port. And we call that a layer 3 or routed port. So if you've got those two interfaces we've been working with in these examples, you could change them to be routed ports, but they've both got to be the same. They've both got to be, or all have to be switch ports, so they all have to be routed ports. So let's talk about 2 examples. Let's just assume this same design with only 2 links. We're here on switch D1, and we do this popular command, show ether channel summary, and it's got these flags listed up in the top for the first dozen lines or so. And then at the very last line, it will list your port channel 1, PO1, and give you these single letter codes down here at the bottom. And you'll notice gig 1013 and gig 1014 with the letter P highlighted. So if you circle back up to the top, it says P, bundled in port channel. So bundled in port channel means this. It means this port passed the local switch's checks of all those things that must be true and correct and match for it to be functional and working and used in this ether channel. So A+ working, in use. Whereas S, suspended, says, hey, we tried those checks and this port is not functional. So this output was taken from example 3 when everything was great. All right. Also highlighted down here, it says SU, uppercase S and U for the port channel itself. It says it's a layer 2 port. In other words, I've just defaulted it to continue to act like a switch port, and the port channel is currently in use. Now, just to contrast that, if we go to example 4's config, where I purposely left off those 2 interface subcommands, like the one for the native VLAN being 3, interface 14, the one that left out those commands, it's got this S, meaning suspended. That's the one where the interface subcommands didn't match up. By the way, this video is sponsored by me and my books. If you don't happen to have them yet, and you click that link or scan the QR code and go to my link tree and click the products link there and buy the books there, you don't have to spend any more money, but those sellers happen to give me a few dollars back from the sale. It's a great way to say thanks and support the channel, and I'd very much appreciate it. All right, back to the content. So for quick review, no matter how you configure an ether channel, static or dynamic, the local switch does these kinds of checks, all right? So this is not extra that's enabled by using LACP. Now let's talk about LACP. If you configure the channel group command with the active and passive keywords, you're implying that you want to use LACP, and LACP will do this dynamic negotiation to decide if a link should be placed into an ether channel. And that dynamic negotiation is looking at additional factors beyond that set of things to consider that the local switch considers, all right? So configuration wise, just on the channel group command, you need one side to be active because it's the one that initiates the negotiation. So you could have active and passive, passive meaning it'll wait for the negotiation to be initiated, or you could have active, active, either way. So active, 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 passive, But passive-passive doesn't work because both sides would be waiting. All right, so what is LACP checking for in addition to those earlier checks? Well, it's going to send these messages. They're called LACP DU messages, and it's checking, hey, are these the same two switches? Like, it's got to be D1 and D2 in this case. It can't be D1, D2, and a third switch, D3, if you will. Are the ports in a consistent ether channel? I'm going to show you an example where here on switch D2, it's got port channel 2, but then the second port's in port channel 3. They've all got to be in port channel 2 on the right and all got to be in port channel 1 on the left, for instance. There's also a keep alive mechanism tied to these PDUs so that the two switches know when the other switch has gone away so they can bring the link down, the port channel down, and converge more quickly. Honestly, I don't go into this kind of depth in the book on what LACP does behind the scenes to do these checks, but let me walk you through a few scenarios just for fun here. Let's say we intended the design on the page here, the one we've been going through throughout the video, but instead of cabling it correctly, we cabled that second link over to a second switch, D3. Well, LACP would discover that and say on D1, this second interface would be in a suspended state rather than a bundled state and not be used for that point in time. Whereas if we had just used static config with the on keyword, D1 would have placed this port in a bundled state and try to use it. Another example, maybe we had this topology drawn and the cable is cabled to the correct switch, it's just to the wrong port in that switch. So instead of port 1016, maybe we plugged it into port 1021 by mistake. So with LACP configured, those messages would figure out, hey, wrong port, D1 would leave its port 14 in a suspended state. Whereas if instead we had gone with the static config with keyword on, D1 would have bundled up port 14 and tried to use it. So as you can see, using LACP in this dynamic method is superior in this case because it helps you avoid using a link that just won't work and dynamically figuring that out and avoiding the mistake you made with your cabling. Just one more, let's say you made a configuration mistake and you typoed your channel group command to use 3 instead of 2 on this second port. Well, that's yet another mistake that you shouldn't make, but if you did make it, if you used LACP, then say here on D1, this port would not be bundled and used, it would be suspended and not used. It'd be yet another check that would be made. The configuration itself is pretty straightforward from what you've already seen. So if we want to configure the same way we did before with static config and just use LACP, you could go over to switch D1 and use the same channel group 1 command, but with mode active on both of the physical interfaces. When the first of those channel group commands was executed, the switch would create the port channel interface. Same thing on switch D2. You could use active or passive there. Again, active and passive imply LACP, but we chose passive here. One or the other side has to be active at least. And the first use of the channel group command here creates the port channel interface by the same number, and we chose channel group 2 on the right-hand switch just to make the point that you don't have to use the same port channel number, the same channel group number on the two opposite switches. Just like with static ether channel, it'll pick up, the port channel interface will pick up all those relevant interface subcommands from the physical interface. For instance, if you had switch port mode trunk and switch port trunk native VLAN 99 on your two physical interfaces, when you configure the channel group command, then the switch is going to create the port channel interface and pick up those same two commands. Those are some of the ones that have to be consistent for both ports to be added and bundled into the channel and be functioning. And just to be complete, we've got the same effective thing on switch D2, except we're using channel group 2 and we're using two different physical interfaces. There are a lot of show commands you can look at for ether channels. So for a config backdrop, it's the same config I just went over for LACP at the very end of that previous section. So we've got a switch port mode trunk and a change to the native VLAN on each of the two physical interfaces. Channel group 1 mode active on the left-hand switch, channel group 2 mode passive on the right-hand switch. So they're both using LACP. They both dynamically create a port channel interface that picks up those same two subcommands. So what do the show commands look like? Well, let's go through a few. First off, show running config reflects that same config. The port channel interface shows up at the top. And in case you hadn't noticed it, the channel group command doesn't get copied up to the port channel interface. It's implied by having the same number, port channel 1, as the channel group subcommands have on the physical interface. That's the only real oddity there. Next up, show interfaces port channel. So iOS dynamically creates this port channel interface. You could have typed it in to create it as well. But you can do a show interfaces port channel just like you could for any other type of interface. And you get the same kind of stats and information that you would with other interfaces on this same command. Things that are a little different, the bandwidth on a physical interface shows the literal speed, the encoding rate on the interface. But here we have a port channel with 2 active 1 gigabit link. So the bandwidth shows us 2 gigabits, 2 million kilobits or 2 gigabits per second. And it's got an additional line that says members in this channel, and it lists the 2 bundled interfaces that are currently working in this channel. So that's another way you can check that. So watch for that. Next up, it's a brief bit of output, but show EtherChannel shows us there are 2 bundled ports right now and that we're using LACP rather than static or PAGP. Next up, my personal favorite for a quick look at an EtherChannel, show EtherChannel summary. It's the one with this dozen lines or so of flags to refer to, and then this line at the bottom that will list the ports that are currently bundled or not, and give you that status of P to mean it's bundled or S to mean it's suspended. And that's a great place to start to see, hey, what's the current health of a particular Ether channel. Next up, show Ether channel, but instead of summary, you give it the keyword port channel. So one of the things that's interesting about this, it tells you the number of ports and that it's using LACP, but the total output doesn't fit on the slide. So up here is what would be down here at the bottom, it just doesn't fit. And that's where the good stuff is. It lists 1 line each for the different ports, and it lists their current state, whether they're active or suspended. So you get a more specific view. And I didn't highlight it here, but this bit here, it says time since last port bundled, and it gives you a time and the port. So if you're troubleshooting, you think, when did the last thing change? You can see that and see which port was the most recent one to get added to the bundle and how long ago it was. So you can say, oh my goodness, 5 minutes ago, this port got added to the bundle. There was a problem 5 minutes ago, and that'll give you a clue of where to go from here. What else? Well, show spanning tree. Remember, we started out talking about this because we had a spanning tree feature that was getting in our way when we added these multiple parallel links. So show spanning tree for a VLAN. Here's the port channel interface that shows up instead of the underlying physical interfaces. It's got a designated port role. It's in a forwarding state. So spanning tree is acting on the port channel, not on the physical interfaces. As a result, the MAC table lists port channel interfaces and not the underlying physical interfaces, with that bit of additional logic underneath it to load balance the traffic across the physical ports. So you're in my study group. What's my advice for Ether channel? Well, first off, no matter whether it's static or dynamic, the local switch is checking those local config settings. Be aware of those and try to memorize what those checks are. Then LACP checks additional things. Those are dynamic, but that's a good thing. We definitely want dynamic Ether channels because of those additional useful checks. And there's a lot under the hood here. You'll probably see that in your CCNP enterprise studies, so watch for that. As for more practice, you should lab this for sure. I don't have videos for this lab as of right now, but here's the direct link to the first Ether channel lab at my blog. It's called EtherChannel 1, and it's got 3 obvious Ether channels in the design. And the lab says configure 1 static, 1 PAGP, and 1 with LACP. And even though I didn't go over the PAGP, I think the lab gives you enough to where you can figure it out from there. Then, as usual, using the book and using that for review is very useful. And speaking of review, we're at the end of a book part. So we just finished up topics that correspond to part 3 of the Volume 1 official Cert guide. And for part review, by the way, all those parts end with a small few pages that suggest what you should do to review the topics in those parts. But it's pretty good and even better for you if you'll give yourself some space. Wait a couple of weeks. Go ahead and get into the next topics and start learning those. Maybe a couple of weeks before you do part review. So next week, for those of you that are watching this, the day or two after I release this video, I'm going to release some relevant videos and talk to you about part review for part 3. And I'm going to release a new lab that's basically a comprehensive lab for chapters 8, 9, and 10 about VLANs and VLAN trunks and spanning tree and the like. And just point you back to the part review questions in the books for those of you that have those. So you'll have plenty of part review exercise to do over the next couple of weeks if you embrace this idea of giving yourself a little time and space before you do it. So for the videos on the screen, watch for them on the left. About a week from today, there'll be a part review video. You can watch that for some context and direction. And on the right, there'll be the Config Lab intro for this new big lab on everything in part 3. Hey, thanks for hanging out. I'll talk to you soon.